I'll be talking about dynamic posture manipulation during tumbling for closed loop heading angle control. My name is Adarsh Salagame. I'm a PhD student with the Silicon Synapse Lab at Northeastern University, and I work with Dr. Eric Sihite with Caltech, Dr. Gunnar Schoner, and Dr. Aliraza Ramzani from Northeastern University. So this work deals with closed loop control for tumbling locomotion. Uh, As you can see in the slide, there's different kinds of robots, each of which use a different modality for generating this rolling motion. Some, such as the spherical mobile robot and Kickbot, use wheel-like structures. In the case of Kickbot, these hemispherical um, sides are wheels that it can use to navigate, whereas others, such as Autobot and NASA's Tensegrity robot, uses posture manipulation for generating this rolling uh, locomotion. At the center here is Northeastern University's COBRA. This is the platform that I will be focusing on. COBRA is one of the few examples that uses dynamic posture manipulation to control its heading angle at high speeds. This is COBRA. It's a multimodal slithering snake robot. It consists of 11 joints and 12 links. Uh, the middle 10 links are all identical, each with their own power supply and servo. The 11 joints are arranged such that the alternating joints are at 90 degrees to each other. So you have a pitching joint and then a yawing joint and then a pitching joint and so on. Each joint is actuated by a single dynamically servo, and this is daisy chained through the robot, controlled centrally from a Raspberry Pi placed in the head. COBRA is a multimodal robot. So, in addition to the tumbling locomotion, it has several kinds of snake-like gaits, including sidewinding and lateral rolling. But in this work, we're mainly focused on the tumbling locomotion, where the snake can actually raise its head and tail and lock them in place together. Uh, to form a ring-like structure which allows it to roll down slopes at uh, high speeds. This is a closer look at the way that COBRA goes into its tumbling configuration. So it raises its head and tail up and aligns them together such that the head goes into this docking module on the tail. It has a single uh, gear in the head that actuates these fins, which go and sit inside this cavity in the tail module, locking it in place passively. And once this is locked in place, it's able to passively hold this without using a lot of energy. Um, and what we want to do with this is while COBRA is rolling, it can actuate its joints to change its posture about its center of mass. And using this posture manipulation, we want to be able to roll down a slope following a desired path down, as shown here. To simplify the problem a little bit, we consider a smooth plane inclined at a fixed angle alpha. We don't consider any irregularities on the slope, and we don't consider a changing slope angle. So we model COBRA as using this reduced order model. We model it as a line mass arranged in an elliptical ring, as shown here. Uh, we make the assumption that the cross section of this ring is negligible, so that makes it a line mass, and that the mass is distributed uniformly throughout, which puts the center of mass at the center of this elliptical ring. And for actuation and posture manipulation, to make the problem simpler, we consider symmetric posture manipulation, so such that the center of mass is always aligned with the center of the elliptical ring. We consider four frames of reference. The inertial frame is the world frame within which we measure the movement of the robot. The contact frame is at the point of contact with the ground. This is perpendicular to the slope and defines the robot's heading angle. The gimbal frame is placed at the center of mass or the center of this elliptical ring, and it defines the robot's pitch angle. The gimbal frame is always in the plane of this elliptical ring. And the body frame is located along the gimbal frame, but it also rotates about this rotation angle, and this defines the role of the robot. So together, these Euler angles, the roll, pitch, and heading are able to define the orientation of the robot, and the vector to the center of mass, PCOM, in the inertial frame defines the position of the robot. So with this, we define the tumbling dynamics as shown here. This is a simplified equation, so we can define the change in the state of the robot, which is defined here as the three Euler angles, roll, pitch, and heading, the rate of change of these Euler angles, the position of center of mass, and the velocity of center of mass in the inertial frame, as a function of the current state and the inertia of the robot. So given this, we can define the posture manipulation dynamics. So the inertia of the robot is a function of the shape of this elliptical ring. And we can define that using two control inputs, U1 and U2, which define the two major and minor axes of this elliptical ring. And this follows this dynamics, which I will talk about in the next slide. The posture manipulation dynamics. So we define the two control inputs, U1 and U2, as the two axes of this elliptical ring. Given that this ring represents a snake robot of fixed length, the perimeter of this ellipse is fixed, which means that as U2 contracts, U1 must expand to keep the overall perimeter of the ring fixed. To capture this constraint, we use this approximation of the perimeter of an ellipse, which makes use of a differential element of length dp, um, given by which makes an angle d theta at the center of this ellipse and forms an angle theta with the gimbal frame axis. And if we integrate theta over 0 to 2 pi, we get the full perimeter of the ellipse. Taking the differentiation of this, we get p dot equals the square root of a squared cos squared theta plus b squared sine squared theta times theta dot, which, given that the perimeter is fixed, this must be 0. So this establishes a relationship between p dot and theta dot. And using that, we can actually define the relationship between our control inputs U1 and U2 and the overall inertia of this elliptical ring. So for this differential element dp, given that we are considering this as a line mass of mass m and total length p, the mass of this differential element must be dm, and we can take the standard inertia formula for calculating the inertia as dm times r square, integrate that over 0 to 2 pi, and substitute this to get a relationship between our control inputs A and B, which we uh, are calling U1 and U2, um, and the inertia of this elliptical ring. The inputs that we are considering for the study, uh, as I mentioned earlier, we consider symmetric inputs about the center of mass, such that the center of mass is always located at the center of the ellipse. So given that, we consider a step input and an impulse input, where the vertical axis of the ellipse goes up from a length of 0.3 to 0.4. And in the case of step input, it stays there. And in the case of impulse input, it returns back to 0.3 within a certain amount of time. Uh, to form these inputs, we use a sigmoid function and a derivative of the sigmoid function that lets us control the time and the rate at which these inputs change from the initial length to its final length. And we also consider a special form of tumbling locomotion called shape invariant tumbling locomotion. And this is what that looks like. So in shape invariant tumbling locomotion, as you can see, as the robot rolls and the input is applied, uh, with the step input, as the length changes, it holds this new shape as it rolls and rolls within this shape. So to an observer in the inertial frame, the overall shape of the robot is fixed with respect to the rolling. So that's why we call this shape invariant tumbling locomotion. And what this lets us do is configure the inertia of the robot about the center of mass in a desired configuration. And that affects the tumbling behavior and lets us control the heading and the speed of the um, tumbling locomotion. So to solve this problem, we built a MATLAB simulator, which uses ODE45 to integrate the dynamics that I presented in the previous slides. And this is the result of those experiments. So I'm going to play this video in a second. This is playing at 0.5x. And on the left here, you see how the elliptical ring behaves without an input applied. And this is the same trajectory that's transposed from this test. And in these two videos, you're going to see how the robot behaves differently once the specified input is applied. So without the input applied, it follows this path. In the case of the impulse input, once the input is applied, you can see that it changes its heading angle, and there's a slight deflection in the path of the tumbling locomotion. And in the case of step input, uh, it actually increases its speed of locomotion as this axis increases. These graphs show the behavior of the robot as different inputs are applied. So this is the XY plot of the center of mass of the robot. You can see the path followed by the center of mass without an input applied. We applied different sizes of impulse inputs, going from 0.3 to 0.35 and also from 0.3 to 0.4. And we vary the rate at which the axis length changes as well. And the larger the change in axis length and the sharper the change in axis length, we see a increase in the deflection of the path. so a larger change in heading. These graphs on the right show the change in linear velocity. Um, so the linear velocity along x is in the direction of rolling. And as you can see here, as the control input gets sharper and as the axis length increases, the linear velocity increases as well. And as it returns to its original axis length, this goes back to the original linear velocity. With this work, we have demonstrated the ability to control heading angle and tumbling speed using the chosen control actions, U1 and U2, which affect the axis lengths of this reduced order model. Um, and we have built a modeling framework that lets us control this tumbling locomotion. The next step is to actually use this model, dynamic model that we have developed to close the loop and follow a desired trajectory and implement this on hardware, which will also involve developing a contact estimation in order to actuate the shape invariant tumbling locomotion. Finally, thank you for your attention. I just want to mention that this work has been supported by funding from NASA's Advanced Concepts Program, NIAC.